Hi there, I present a new algorithm called Projective Cutting-Planes. For semi-definite programming, it is most effective for dense and easily feasible instances. What's the main idea? First, imagine we had the feasible area like a polytope P with prohibitively many constraints. I recalled that the SDP feasible area can be defined or expressed, if you want, as a polytope with infinitely many constraints. I need to introduce the standard cutting planes for such problems. The idea is that I have too many constraints. So this algorithm is very well known in the literature. At the very first iteration, for instance, if I maximize an objective function in this direction, let's say I only have two constraints. This means that the first polytope only contains two constraints. It's an outer approximation of the real of the feasible area opt P1. It's the solution of this outer approximation of the feasible area, and by separation I capped this outer solution opt P1. I find a smaller polytope P2, then a smaller one P3, P4, opt P4 moved here, and if I continue this way, I find in this example opt P6 here, which is actually the feasible, the outer solution is feasible, so this means it cannot be separated, and I have the optimal solution over the polytope P. I propose the idea of upgrading this separation subproblem to a projection one. The projection will also generate interior points in the feasible area, but I will still keep these outer solutions. Here I mean objective values. Opt P1 is larger than opt P2. The optimal solution value is smaller and smaller. This is the first iteration. Imagine I know nothing about my polytope or SDP feasible area. The best thing I can do is to start from some feasible solution. Let's say here is the origin to make things simple. And if you want, I project it to follow the direction of the objective function. In very simple terms, imagine that here I'm a feasible point in this room, which can be seen as a polytope or feasible area, and I fire a bullet in the direction of the objective function B. I fire a bullet towards the sky, because if you want, I don't see all constraints, or they are too many to have enough place in my mind. And if I fire a bullet, it will stop in some point that I will call a first hit point. Y1 is the first starting point, if you want. D1 is the first direction here, the objective function. And the bullet will stop here. The bullet will hit some facet of the polytope, or if I have an SDP feasible area, if you want a tangent to the SDP feasible area, and now I pay attention to this facet, and I can put it in my mind. I have enough place for it in my mind, and this will help me determine a first outer approximation P1 of the feasible area. The outer solution is opt P1. The next step, I will project this guy, which is a feasible point, because here everything between the basis of the last projection and the last hit point must be feasible in a convex body. And I project, let's say, the midpoint between these first 2 points towards the outer optimal solution, opt P1, the best outer solution I know up to now. Why? Because I want to reduce the gap between these two solutions. This is an upper bound, this is a lower bound. I need to know how they relate with regards to the feasible area, which one of the two is closer to the boundary of my feasible area. Let's say I find this facet, this new hit point, the optimal outer solution moves here, then I continue, I choose Y3, I project it towards the best outer solution I know up to now. I obtain, let's say, this constraint, linear constraint, a new feasible point, and here, if the polytope is this gray area, the real polytope, opt P3 will become optimal, and I can no longer separate it. But by projecting this last iteration, I will obtain the feasible, the fact that this point is feasible, and then optimal. The convergence proof is very short, because at each iteration I separate even by projection. The projection generalizes the separation. I separate some opt pi outer solution, and for this I retrieve a new constraint of my feasible area. So even for an SDP feasible area, like in this image, it's not a linear one. What I want to mean by the fact that the problem, the process is convergent, for all practical purposes, the amount of memory on this planet is finite. So for all practical purposes, if you are happy with the memory available on this planet, you will solve this problem, even the SDP1 in practice, considering a finite number of constraints, even if huge. The convergence proof is quite short if we see it this way. It was not always like that. I worked on this projection idea for about more than 10 years. In the initial paper, the proofs were longer. The new method was designed on purpose to be more general and even more simple. This is a quite tricky goal, to do something more general or to do a simple and effective algorithm that it remains quite simple. So it's not happenstance that the proof is quite short. The previous papers I worked around this idea have been devoted to linear problems, even if with a huge number of constraints. Please notice that both for the linear case or for the SDP case, I have a trajectory in red of interior points. At the same time, I have the blue outer points that converge with the red ones, if you want. The trajectory of these inner points are a driving force of the algorithms, because they are seriously taken into account when finding new facets. This is a feature that does not exist in other cutting planes algorithms. I mean, even in some cutting planes algorithm, you may always find some local problem-specific ways to find inner solutions while performing cutting planes. They are usually a byproduct of the algorithm. Okay, everything was a bit like in a movie up to here. What is the difficult part is solving the projection, so more on that later. Let me now introduce the SDP problem. Let's say I have a k variable y, and I work with this k plus 1 n by n matrices. Let's say I want to maximize this under the constraint that this x is SDP. I have a linear sum of matrices. This constraint is equivalent to this one. I write it in a linear form if you want, because I want this guy to be non-negative for any vector in my space. What is this big dot operator is well known in SDP programming, is this sum. You notice is a sum over is a weighted sum over all elements of x, weighted by a fixed value as long as v is fixed. Let me work it a bit. Sorry for the experts here, you can skip some minutes. But if I have such constraints, recall x is this, recall the big dot operator is this, and the SDP constraint in gray is satisfied if and only if this is true for any v. So here I only replaced x with its value. By simply rearranging the terms, I can write it this way, and then I obtain that the matrix is SDP if this eigencut holds for any vector v, column vector v. And here I have the big dot operator on the right hand side, and here each variable yi is multiplied by this value. During the cutting planes framework algorithm that I will propose, I will generate many vectors v, and for each time I generate a vector v, I need to pay in computational terms the calculation of this guy and of these k guys. Let me write the problem this way. We could address the problem by separating at each iteration some infeasible y. How can we separate? By simply finding the minimum eigenvalue and the corresponding eigenvector for the associated X matrix. Such standard cutting planes is not considered very effective. Work on such idea is limited. But the cutting planes framework has some interesting advantages that do not exist in interior point methods more popular for solving this kind of problems. Imagine that at some moment I generated some V, and if this cuts V do not cover all space R power n, I have a standard LP here. Please look, and I can compute the dual by associating to these constraints dual variable alpha V. I speak about dual LP. Okay, and if I compute the dual constraints, I have one constraint for each I from 1 to k, I mean for each variable yi, and if we pay attention, take some minutes if you want to verify the calculations, I obtain this constraint. And here, by summing up over all V, and since alpha is positive, actually I obtain an SDP matrix. So the dual LP solution will give and if you do all calculations, it's not very complicated to see that this matrix Z will become an SDP dual solution in the dual SDP. So thanks to using the simple LP duality, we can associate a dual SDP solution to the outer solution, you see, generated by these cuts of the current LP, considering the currently generating cutting planes. So, thanks to this feature, the new method will generate at each iteration a feasible solution inside the SDP area and the feasible dual Z, which is something an interior point method cannot do. I mean, for an interior point method, I will use the name IPM. If you stop an IPM before finishing, I think, I know actually, that you have nothing. There is warm starting work in this area, but it's very, very difficult to generate a primal and dual feasible solution along the way. Now, let me go back to a figure similar to the one presented some 7 minutes ago. Let's say this P is the SDP feasible area. So I have Y3, which is feasible. Opt P2 is the outer solution computed only on the basis of the currently generated constraints by optimizing over the constraints I know up to now. And here, if I project, I obtain a new constraint. And in this example, I have the small square is a new interior point, feasible solution, and the circle will give me, as I said in the previous slide, a dual feasible solution. So here the primal and dual feasible solution almost close the gap. What is difficult? Solving the SDP projection. I recall the problem I want to solve. So here, don't forget that the variables y also live in a polytope. What do I mean by that? It's the first time I focused on this notation. I can have a set of linear constraints. A constraint is given by the right hand side CA and by the coefficients A of the y variables. And I have a set of constraints and I impose these. These are not strictly speaking SDP constraints. Okay, but what I want to focus on now is solving the projection problem only over these constraints, because I consider these linear constraints can be enumerated in practice. What happens? I need to find the maximum T stars such that this guy remains in the feasible area. So, with regards to the SDP part, I want the maximum T such that X plus TD stays SDP, where X is defined as explained on some of the previous slides, which is SDP when Y is feasible, and the D is defined in a similar manner. It can be SDP or not. It's indefinite. So, I need to solve this. The problem is surprisingly easy if X is strictly SDP. In this case, I have a unique Cholesky decomposition where K is non-singular and triangular. Looking over this formula, if you want, if I replace X by K transposed, I wonder if I can do a similar, if I can apply a similar idea on D. And let me try to solve this system in variables D prime, and I can always solve it using a few back substitutions because K is triangular and non-singular. So I will obtain that these two guys are completely equivalent thanks to a rewriting, and these guys are equivalent because the SDP status of a matrix is the same, does not change if I multiply that matrix by K on the left and K transpose on the right. So the final idea reduces to solving this problem, where I have the identity here, and take a few minutes if you want, but this reduces to computing the minimum eigenvalue of D prime. What is the total projection cost? One Cholesky and a few back substitutions, one minimum eigenvalue. I need to compute products VV transposed and also K plus 1 products of this form, because I install eigencuts of this form. So once I determine a V, I need to compute VV transposed, and then this is a dot product, and I have K dot products here also. Okay, the complexities are given here, but they do not have much impact on the reality, because at least in my MATLAB implementation, most of these operations are really much faster than what this may suggest, at least when I compare to an interior point method that needs to compute at each iteration a so-called Schur matrix, which asks for this complexity. However, the calculation behind this are crazy compared to performing a dot product here. This involves operations much more complex than the below one. So in practice, this is very simple, while this is very complex. Yet, some of the solvers, like Mosaic, I think they invested crazy time to find ways to accelerate it and to exploit sparsity. But still, generally speaking, this work is motivated by the fact that I think for a big N, let's say above 2000, computing this matrix will make interior point methods run out of gas. Okay, still, this is a projection cost in the simplified case where X is non-singular and strictly SDP. This particular case was enough to solve a very first instance, this is how I started, in which all matrices have strictly positive eigenvalues. All generated in interior points are strictly SDP, because I did not start from 0, but from the identity multiplied by some small value. This is such SDP program is a bit the counterpart of an SDP program of an LP program in which all coefficients are strictly positive. I can always find such a feasible solution. The upper bounds of the standard cutting planes need 9.26 seconds because even if it finds the optimal solution quite rapidly, it takes a lot of time, it needs a lot of cutting planes to prove it is optimal. Here Mosaic needed this time 721 and the Cunning bundle needed 2.23. But thanks to the fact that the new method generates both lower and upper bounds, the projective cutting planes converge in 1.15 seconds. So it was my first test that encouraged me to continue. Let's move to the idea of projecting X from some X that has rank below n. I apply the LDL decomposition that will write the matrix this way. This LDL decomposition is usually presented in a matrix form, but is the same if Li is a column vector. And I need to pay attention. Sometimes even the LDL decomposition will give me for some I This is a matrix in which all elements are very, very small. Okay, we need to pay attention to such cases because there may be some approximation errors because of solving previous systems. And thanks to this LDL decomposition, it's very easy to spot data that should be zero. And sometimes the official LDL decomposition is even smaller because some of these terms are even zero. Then I will rewrite it this way, a kind of Cholesky decomposition, only that K and C is no longer a square, it has this size. And I still try to solve this system in variable d prime. If this has a solution in variables d prime, the problem reduces to something very similar to the previous case, to this one. Okay, which is solved by finding the minimum eigenvalue of d prime in the world of C by C matrices. In this case, I can solve this system because D is in the same image, is in the image of X, which is also the image of K and C. So to some extent, somehow we can ignore the null space of X and D. If there is no solution d prime above, this means that some components of d prime are outside the image of X. I need either a few pages of other decompositions. This was the most difficult theoretical step, but I do not have time to present it in a short talk. But let me present another method that can be very practical and easier to understand. If I can only advance by a step of epsilon, a very small one, and still remain as dp, what happens? I can reach T star in two steps. First, I move from x to x plus epsilon d, okay, and I'm still inside the SDP cone, and then there are high chances that d will be in the image of this guy, because I do have some components of d here. So I can solve this second step using the previous approaches. Okay, it may not work always. There are many details behind it, because there are many particular cases that needs to be addressed, and it's a bit more complex than that. In some cases can be very difficult. I mean, I need 1 page or two. I cannot present them in one slide. Let me present results here. The most benchmarks present very sparse instances. I have some example here. This is K, this is N, this is the number of linear constraints in the model. Mosaic is very fast for such instances. I present the time of the new method. As we can see, for an instance like this, it can be almost 20 times slower, let's say 17 times slower. If the instance gets bigger, I can be 50 times slower or worse. So I must confess, sometimes I need to lose. On such instances, I'm not better than Mosaic, which is one of the fastest solvers. But let me densify the instance, because then the story will change. What happens here? Let me replace each matrix AI by this guy. So I multiply AI at the left with M transposed and at the right by M, and what happens? Since M is an orthonormal matrix, it doesn't matter which one, I will obtain a rewriting of the instance somehow in a different space. So what do I mean by that? I mean that the matrix, the new instance is exactly the same, but it's written in a densified manner. And in this case, Mosaic will jump from 3 minutes to 10 hours. Okay, so the power of sparsity is huge. And in this case, with the new method, I can compete with Mosaic. Not to mention that an interior point method will give you nothing before the 10 hours are completed, while I can give feasible and dual feasible solutions even after whatever time you choose. Now I can present more tables of results. They are in my paper. This can be quite boring in a talk, and it's very difficult to make my case, because It's quite tricky to compare algorithms for such a problem. There are at least a dozen of other solvers. They can be faster for some instances, some can be faster for some instances, others can be faster for other instances. The future will tell which one is best, but I can compete, this is clear, because here I only mention Mosaic, which is often considered one of the fastest, maybe not always, but for a short talk I can only refer to the paper for more results. The new method, the method I proposed is most effective for dense instances, and even if I do integrate some heuristics to find a feasible solution, it's more powerful if the instance is easily feasible, if it's not difficult to find some feasible solutions. But let me give a more theoretical argument. Reoptimizing SDP programs, what does that mean? I solve an SDP program, and then I want to add, for instance, a new constraint, because I may have a branch and bound decision if I solve an SDP relaxation only inside a branch and bound framework, and I say the variable y9 is 0. In such a case, the interior point method is not as fast as you may know in linear programming, performing a simple dual simplex pivot. It's very difficult to reoptimize. There is warm starting work for interior point methods, but this is very, very difficult. We need a lot of work. Mosaic, for instance, it cannot do it. I'm not aware of software that can do it. But the cutting planes nature of the new problem can make it work for these kind of problems, because what means I insert a new linear constraint in my model. What's okay for the cutting planes? I have a new constraint like for all others. What happens, for instance, if I play robustness over the LP part? I have other papers in which I explain how I can solve the projection subproblem over the infinitely many constraints that can apply if I allow the coefficients A to vary according to robust rules. I already designed an algorithm for that in this linear programming context. So I end up with a program in which I have an infinite number of constraints for two reasons. The SDP one, and second one, robustness over the LP part. For such a case, I don't know how I can use an SDP program without needing to solve at each step. Without needing to restart the solver after adding each new robust constraint. And I have some results for some instances. I have a nominal optimum problem. The robust one is smaller. Projecting cutting planes for these instances can perform only a few iterations. They integrate along on the fly the robust cuts, the same way they integrate eigen cuts. But if I use an interior point method, Mosaic or Sedumi, the solver calls, I need to call the solver multiple times, you see, because I don't know how to restart from scratch, how to do it without restarting from scratch. So I solve an SDP program, I add a new robust cut, which is a modified version of this according to some robust rules, and then after adding this new constraint, I need to restart the solver. And let me conclude. I just want to say that the new method actually works over a large class of polytopes. This is my previous work that I mentioned in linear integer programming, but it's my first work where I applied the method over the SDP feasible area. A driving force, it's a sequence of inner solutions that do not exist inside the cutting planes. Actually, on the SDP case, there is only about 6, maximum 7 papers that tried the cutting planes to solve it. So there is no mention of inner solutions. That's clear. So the new method, a strong point, it generates both the primal and the dual SDP solution at each iteration, something an interior point method cannot do. And I have hope to beat the interior point methods if n is above 2000, because I think in such case IPMs will run out of gas for dense instances, or for sparse instances. According to my tests, if n is bigger than that, they tend to become really slow and very, very, very memory intensive. So even if the instance is sparse, if it is so big, I noticed that Mosaic, for instance, may need more than around 100 gigabytes or even more to solve the problem. So if there is not enough space, the new method can also be better. Thanks for watching. Bye bye.